Good afternoon, everyone. I'm Chen from Shanghai Jiao University. Today it's my pleasure to present our work, UEFI, a microkernel-style UEFI with isolation and transparency, which targets at addressing the growing risks in firmware security. Let me begin with a brief overview of UEFI. UEFI firmware is responsible for initializing hardware and bootstrapping the operating system. Most drivers are loaded and initialized during DXC phase, which constitutes the main execution environment of UEFI. After the device drivers are ready, control transfers to boot manager and bootloader to select and boot the OS. From the OS perspective, UEFI also serves as the root of trust, ensuring that the system starts from a known good state. The security phase is the first stage of UEFI, where a small piece of code measures the integrity of subsequent firmware components. In recent years, we've seen emerging cases of real-world attacks targeting UEFI. For example, Moonbounce and Black Lotus show that attackers can implement persistent threats in firmware and even bypass secure boot. Black Lotus was even sold on hack forums for $5,000, highlighting its sophistication and impact. Once compromised, UEFI firmware allows attackers to gain control over all subsequent boot stages, enabling them to manipulate the operating system from the very beginning. Let's look at a more concrete example, logo fail. It was a critical vulnerability affecting many major vendors. The root cause of logo fail is actually quite simple. During system boot, if a crafted logo file is loaded with specific image weights and image height values, it can trigger an integer overflow. As a result, the driver allocates a buffer of the wrong size. When it later tries to access this buffer, it causes a heap overflow, and subsequently causing arbitrary rewrite. Logo fail drew a lot of attention, not just because it's a data-only attack that can bypass secure boot, but also because it remained exploitable more than a year after it was first disclosed. This shows the difficulty in patching firmware vulnerabilities in time. To better understand the risks, we analyzed recent CVEs related to UEFI and tried to answer two quick questions. What kinds of bugs are common in firmware and why do they lead to such serious consequences? Our analysis shows that memory safety issues and improper input validation are the most frequent and severe. One notable pattern is that improper input validations often lead to out-of-bounds reads and writes. So, why are these bugs so damaging in UEFI? We summarize three main reasons. First, UEFI runs in a highly privileged environment. Any malicious code could have deep control over the system. Second, UEFI modules share the same address space and there is no isolation between them. That means a bug in one module can easily affect others. Third, UEFI uses coarse-grained access control. Once a module passes secure boot verification, it gets access to most of the firmware resources. These factors together make UEFI vulnerabilities especially dangerous and hard to contain. The problems we see in UEFI take us back to the long-standing debate over OS architecture. Monolithic kernels places device drivers, file systems, and core logic all in the same privileged environment. In contrast, microkernel flips that module, core stays minimal, while drivers and other components run in isolated user processes. This separation delivers stronger security and full isolation. What's interesting is that the philosophy of microkernel addresses the problems we saw in UEFI, and it also aligns well with the modularity and extensibility design principle of UEFI. So we saw, why not apply the microkernel architecture to UEFI? Let's throw the large number of modules to user space and confine their bugs in their own sandboxes. Although microkernel and UEFI seem to be very matched, there's one more key requirement we have to satisfy. The framework must be transparent to existing modules. First, isolation must work with drivers we can touch. Many third-party drivers are shipped without source code. Only binaries are accessible. We also need to support option rooms, which are essentially firmware images stored on external devices. Since they are discovered and loaded at runtime, we cannot analyze them offline and we cannot modify them. Second, modifying existing modules can be practically difficult due to the large number of existing modules on diverse devices, and the production firmware often comes from a long supply chain. Achieving module transparency brings two major challenges. The first is transparent control flow transfer. In UEFI, modules can call external components only in two ways: services and protocols. Services are a fixed set of APIs provided by the UEFI core. They offer basic functions like memory allocation and event creation. Protocols, on the other hand, represent more diverse capabilities implemented by the modules. They are dynamically installed by one module and discovered at runtime by others. For example, a disk I/O driver installs a disk I/O protocol during its initialization. Later, the fat driver tries to get access to disk read-write operations. It looks up the disk I/O protocol using a specific GUID to get the protocol interface. Both services and protocols are accessed through function pointers, but in the microkernel-style system, direct function calls are not allowed across isolation boundary. We need to use inter-process communication instead. But here's the catch. Since protocols are discovered at runtime, we don't know in advance which interface will be used. That means we cannot statically analyze and rewrite the binaries ahead of time. The second challenge of module transparency comes from data plane. UEFI modules used to assume unconditional data sharing. With the separation of address spaces, data passed with pointers cannot be directly accessed by other modules. To address above challenges, we analyze the loading and execution process of UEFI modules. We find that there is a central data structure in the lifetime of all modules, the system table. System table is passed into modules as a parameter of module's entry point, and it acts as a kind of call-out gate. It contains pointers to all the core services, and only through those services, modules can install or acquire protocol interfaces. So we leverage this unique call-out gate to manage sandbox modules dynamically. Instead of giving each module the original system table, we pass it a shadow version where the core services are replaced with system call stubs. These stubs redirect calls to our shadow services. On top of this mechanism, we can enforce fine-grained access control, similar to seccomp in Linux, and restrict what services and protocols a module can use. Now let's look at protocol interfaces. Since mEFI controls both protocol installation and lookup, we can take this opportunity to dynamically generate and inject protocol trampolines for each protocol function. Whenever a protocol is installed by one module or opened by another, we generate a custom trampoline for that specific function. The first one is injected into the core, allowing the core to call protocols implemented by sandboxed modules. The second one is injected into the requesting module. These trampolines are generated on the fly as machine code, and they are tailored to each protocol function with hard-coded protocol GUID and function pointer offsets. Here's how the trampoline mechanism works in practice. When a module calls a protocol function, it actually calls a trampoline generated by its shadow services. The trampoline first saves the arguments and then redirects calls to the sandbox manager. With the help of trampoline, we can intercept and reroute control flow without modifying the original binary at all. After solving the challenge of control flow transfer, the next question is, how do we synchronize data across isolated modules? This problem has been extensively studied in OS-level driver isolation. Previous systems like LXFI and KeySplit explored ways to automatically isolate drivers, making great efforts in handling shared states. But UEFI is quite different from a traditional OS. Programs run concurrently in OS, but UEFI takes a single-threaded execution model, so we don't need to worry about concurrency locks or automatic operations. We also noticed that protocols have clear definitions, allowing developers to rely solely on their interface contracts without requiring knowledge of the underlying module implementations. Protocol function parameters are annotated with in and out indicators, clearly specifying which arguments are inputs, outputs, or both. Besides, UEFI specification defines more than 200 standard protocols. Modules supplied by different vendors adhere to the standard protocols. These characteristics of UEFI make it possible for us to automate data transfer without analyzing driver source code or binary. Next, I will show you how we actually make that work. Before we get to the runtime, we need to first retain type knowledge. Although the core stores pointers for all protocol interfaces, it has no idea which pointer belongs to which protocol, and it certainly doesn't know the structure or layout of the data involved. So we perform offline analysis on protocol headers ahead of time. We extract and organize the information into three tables: protocol, function, and type. Let me walk you through a concrete example of cross-isolation data transfer. Suppose we have a product function with two parameters. The first is an input pointer, and the second is a two-level output pointer. Here's how the process works. Initially, the input pointer refers to a data buffer owned by module A. When the product function is called, control is transferred to sandbox manager. It allocates memory inside module B's space, copies the input data over, and creates a transient copy of the input. Then the actual protocol function is invoked. Inside module B, the function allocates a result buffer and sets the output pointer to point to it. After the function returns, the sandbox manager copies the output data back into module A space. Since this output will be accessed later by module A, it's not transient. To avoid memory leakage, we bind the real output and the copied one together. When one is freed, the other is freed in a cascading manner. The final question is, how does the sandbox manager interpret a pointer when synchronizing data? A pointer can refer to many things: a singleton value, a variable length buffer, or an array. Fortunately, UEFI protocols follow a well-defined naming convention for function parameters. We take advantage of this by applying a heuristic we call parameter pairing. For example, parameters named buffer are often paired with parameters like buffer size or buffer length. Once such pair is found, we can infer the pointer's meaning. We apply this heuristic to analyze all protocol definitions in the EDK2 MDE PKG and find that it works remarkably well. Less than 2.5% of all fields could not be automatically analyzed. The fewer cases typically involve implicit semantics between the caller and the callee. We implemented a prototype of mEFI on two platforms, QMU-KVM on x86 and the Raspberry Pi 4 on ARM. We avoid making intrusive modifications to the UEFI core, and we achieve that with fewer than 100 lines of changes to the core itself. Most of the functionalities are implemented in the sandbox manager. To evaluate the performance impact of sandboxing, we first measured and compared the firmware boot time with and without sandbox modules. We selected 6 widely used UEFI modules. The results are encouraging. Running all 6 modules in separate sandboxes introduces only 1.9% overhead during firmware boot. The boot time of OS is not included here, and it's often much longer, which means the overhead can be more negligible in practice. To further evaluate the runtime overhead of mEFI, we focused on 2 frequently invoked and highly interactive modules, the FAT driver and the disk I/O driver. When both drivers are sandboxed, the average overhead is less than 1%. We further substitute the disk I/O driver with a mocked version to exclude I/O operations. Sandboxing FAT in such scenario introduced an overhead of 20,000 of cycles. Sandboxing both FAT and mock disk I/O introducing another 4,000 cycles. To better understand where the overhead comes from, we broke it down by examining the latency of 4 types of protocol interfaces. For each case, we break down the latency into 4 components: the context switch, the protocol database query, parameter copying before the call, and parameter synchronization after the call. We find that most of the overhead comes from data synchronization, and the total cost increases with interface complexity. To summarize, mEFI is a microkernel-style UEFI that enhances security and fault isolation. It enforces seccomp-like access control over UEFI modules. By leveraging the unique characteristics of UEFI, mEFI enables isolation with no need to analyze or modify driver binaries or source code. In short, mEFI shows that it's possible to make firmware execution safer and more robust without sacrificing compatibility or requiring a complete redesign. Thank you for listening. I'm happy to take any questions.